Anytime.
Hello everyone. I'm happy to introduce Dr. Mikhail Tsesarsky from the Ben-Gurion University of Negev. Mikhail has a joint appointment at the Department of Structural Engineering and Geological and Environmental Sciences. And the research interests are mechanics of geomaterials, soil rock and concrete, numerical modeling, seismic ground motion, and engineering geology.
God, people are so
Ginny!
Okay.
Barbara!
תודה, אנחנו נדבר בעברית עד שאנחנו נפתור את הבעיות הטכניות. מה הבעיה עכשיו?
חרא של מחשב, זאת הבעיה. אפל.
נכון, אתה צודק. ועד עכשיו, הנה. ועד עכשיו לא אין לי בעיות איתו.
יאללה, יופי.
Here the screen works. The talk I gave, we couldn't get the screen to come down, so we had the board in between. Yeah. Great big hall.
No.
1001 or whatever it was. Oh,
תן לו.
do you operate at all the console in there?
אם אני מוציא את זה ל-application mode, מקודם ראיתי את
When they're operating, you still have
It was very strenuous. Very strenuous demands on the network. Someone that was really sitting on it would be good, but keeping it without someone that actually does the work. I hope that the application mode is
זה משהו אחר, רגע. יש לך...
One for 200 meters. Then there is an arrow here. The glider. I don't know. This side. This is
I don't care.
This is
We were coming apart.
You know, like in the same day.
we come along with you.
I told you yesterday at the end, everything was fine. They didn't have an answer. I guess there was a
Question is,
I didn't bring anything special, but I can go into sort of system here.
Okay, my sincere apologies for the technical difficulties. I didn't know that.
PDF עבד בסוף.
PDF תמיד עובד. It's portable something. So, thank you for inviting me here. I have to apologize for my broken English. I am bilingual, but my mother tongue is Russian and Hebrew, and English will be the third language that I speak. But I presume that it will be more than enough, and if I am wrong with the head and the has and the tenses, you will have my approval to correct me whenever I go bad. Okay, let us begin with the motivation for this research. This photo was taken in 1997, as you can see by its poor quality. It's not digital photo. And here we can see an event of collapse of a bell-shaped cavern. The cavern is here. I cannot see it because it is in the shade. And it has occurred at about March 1997. Overnight, suddenly, a bell-shaped cavern collapsed. Here we can see the collapse. And being part of a national park with the outdoor archaeological park, with approximately about 250,000 visitors per year, the authorities of the park had decided to go for a study of the stability. In this particular picture, you can see several features that will be common in our talk. First of all, you can see the white chalk, in which the caverns were excavated about 1,000 years ago. Here we can also see this other feature is the surface of a tectonic pre-excavation joint, and almost normal to it, you can see here an irregular surface of a tension joint which has developed during the collapse event. This particular cavern is very small. It's about 16 meters in diameter and about 12 meters high. And it stood almost 1,000 years, and then suddenly it has collapsed. And the question is why, naturally? Why has it collapsed? Why there is association between pre-existing joints and newly formed joints? And maybe the most important question in the context of the Bed-Gubrin caverns is that they are very popular not only for, say, for travelers passing by in 10 to 15 minutes, but also for events like concerts, as you can see here. Some time ago, I don't remember exactly if it was stopped or not, but there was weddings, big weddings inside with music and parties and so on, with hundreds of people staying there for a couple of hours, even sometimes overnight. And the question was, okay, is it safe? The apparent answer to it is no. It's not safe, and here we can see the proof. We can see it here. This is the remains of a collapsed large cavern. Okay, here once was the roof. These are the walls. And sometimes in the past, and we don't know exactly when, sometimes from, let's say, 12th century to our modern time, it has collapsed. So we have now the motivation for the research, and let's talk about the outline of this talk. So first of all, after the motivation, I will introduce the challenges that are associated with rock mass deformation and their analysis. A short introduction about modeling of discontinuous rock masses. Then quite an elaborate description of the Bed-Gubrin case using different methods, independent, starting from deformation monitoring, NanoSeismic monitoring, FEM modeling. I added here some GPR data, and eventually the conclusions will come. This work was done by many people over several years, now almost 15, starting from 1997. Dr. Hillel Buzblo from Tel Aviv University, Eli Machlab, who was my master's student, Dr. Eretz Gal from BGU, Dr. Daniel Fried from Isotope, who has performed the GPR survey, and all the workers of the Bed-Gubrin National Park are very much thankful for the assistance. So we had a rock mass, nice rock mass with some joints, and now it deforms. It deforms because something or someone or anything has perturbed the initial equilibrium. So now we have this material which is called rock, and it is very complicated material, and the reason is because it is not an engineered material. Engineered material comes with a spec. Okay? If I take steel or even concrete, which is in a way is a very complicated geological material, but I don't know what to expect from it. And if I want to make an assessment of the deformation and the stresses at the new equilibrium state, let's say I can use linear elasticity under the assumption that our material abides to a name or to an acronym of Chile. What is Chile? Chile is not the South American state, but it is rather an acronym for continuous homogeneous isotropic linear elastic material, which is a perfect material, for which we have closed-form solutions like elasticity, which can be written in terms of stress and strains, or even elaborated rather more using notations of displacements which do occur in the continuous state of the matter. Now, when we look at geomaterials like rock masses, natural rock masses, they do not abide the acronym of Chile. They go under other acronym, DIAN, discontinuous, inhomogeneous, anisotropic, non-elastic. And if we do assume that they are elastic, okay, and we look again at the same constitutive law between stresses and strains, we cannot use the following notation using displacements, because the displacement within the mass is partitioned between material displacements, and here with the subscript of J standing for joint, for discontinuity, for normal and tangential displacements along joints. Given this state of matter, we cannot use a simple elastic linear or even non-linear approach because of this partition of displacements. So basically we can speak about two non-linearities in materials, in geomaterials. One is related to the material itself. It can be plastic material, which most rocks and soils become plastic under after some strain. But more of it, we have also geometrical non-linearity, which are the discontinuities, the joints, the fractures, the faults within the rock mass. And what are these discontinuities? What do they represent from a mechanical point of view? First of all, across a joint, as we can see here, the stresses are not continuous, they are stress jumps. There are no continuation in displacement. There can be a discontinuity of displacements, and something that is never taken into account using elasticity is rotations. Rock can rotate along joints, along discontinuities. And the important issue when coming and analyzing rock masses is to see what is the scale of the problem, of the perturbation, let's say a tunnel or a cavern, relative to the discontinuities. So basically, if the material or the rock mass is free of discontinuities, we can apply continuum mechanics as is, and this is a very wide and very common approach. If the discontinuities are an order of magnitude smaller than the perturbation, than the cavern, then we are looking at a discontinuum in which we are more interested in the displacements of each discrete block rather than the stresses within. Because the stresses are changing, but the blocks are very small and the displacements are more of an interest. If the rock is totally fragmented, let's say like in proximity of the big fault, then we can use pseudo-continuum, where we just analyze it as a continuum with much lower elastic constants. Main problem remains when the discontinuities and the caverns or the perturbations are of the same scale, of the same size. Because we are then interested both in the stresses within the continuous matter here and the displacements along the joints. And these are not always compatible together. And we have various numerical models that can assist us with solving problems in rock masses, starting with the continuous ones, finite elements analysis, finite difference, boundary elements, and so on. We have methods for discontinuum, like DEM, discrete element methods, FDM, fractal dense network, and also now emerging hybrid methods like FEM, DM, and so on. The continuous methods, the FEM, FDM, BM, are at least half a century around. They are very established, very mature methods, and they can accommodate various features common to rock masses, such as nonlinear material models, plasticity, flexible boundary conditions that are widespread in engineering and in science, but they have one big difficulty, and the difficulty is incorporating discontinuity. They are all methods of continuum. Once we incorporate this continuity, we are now in a totally new world. And Already in 1968, Richard Goodman from Berkeley have incorporated a joint element into a finite element models, where joint elements are elements, very thin elements that are capable of large deformations, but there are no separation or rotation along these joints. They are computationally very intensive. In order to represent even one joint, you need to add many degrees of freedom to the mesh. And if you use too many joints, then the entire numerical scheme becomes numerically unstable. It does not converge. On the other hand, we have the DEM, the discrete element methods which was developed to overcome all of these problems, but they do have compromises, and the main compromise is that they are, first of all, they are very intensive. There is a limit of what you can solve. Naturally, computers are becoming stronger and stronger, so we are now in a much better place. But even a bigger problem is verification and validation. Is this code is solving the right equations and in an accurate manner? And this problem is still an unsolved problem for DEMs, because even the most simplest case of discontinuous deformation does not have a closed form solution to which we can compare our solutions. So with this in hand, we have to analyze the mechanical stability of the bed-covering bell-shaped caverns, naturally, because going to PDF, you are missing the entire animations, but okay, line by line, you can imagine it comes in. So our goal was, okay, now let's analyze the stability of the bed-covering caverns using the most appropriate method for the case, meaning that we can also account also for the joints and for the continuous part of the rock, and look at it at different scales and using different independent methods. So a couple of words about the bed-covering bell-shaped caverns. The entire area of the Shfela is perforated. Okay? Some accounts by archaeologists say that there is more than 1,000 different bell-shaped caverns, individual bell-shaped caverns. The biggest cluster is at the Bed-Guvrin National Park, and it's basically two clusters. One of them, the southern one, is closed for almost 15 years now, but it is quite stable since then. And the northern one, it is the one that we see here. This is the main hole, and it was excavated as a stone quarry. There was quarry chalk, the very soft, the very weak chalk of the Maresha formation from the Eocene. And there's still a debate between archaeologists. What have they done with all the chalk that they have excavated? Because we don't see any buildings built from this chalk. Actually, you cannot build buildings from this chalk. And there was other assumptions. They were making some kind of stucco for buildings, but nobody really knows what has been done with this method. But the endpoint is here. The endpoint is a very large systems of irregular openings, all of them of a bell-shaped cavern. Here on the right side you can see, this is not typical, this is maybe the highest cavern that is found in this complex. It is about 20 meters high, and it's about 16 meters in diameter. Its floor is like an ellipsoid. And you can see here the features that are common to all. It all begins with a shaft, which goes through about 1 meter, 2 meters, a layer of a calcareous caliche, which is on the top of the topography. Once the ancient workers, once they have reached the chalk, they have enlarged it in a radial manner until eventually they have a very nice bell-shaped cavern. The thing is that they wanted to maximize their profits, we all do, and they excavated many caverns, many caverns, eventually overlapping each other. And what is left now, it is a very big structure. This one is about 14 individual caverns with some undefined geometry of supporting pillars. You can see one here and one here, which I'll relate to them later on. And different levels. It's not, everything is not on the same level. This is one level. This picture is another level. with that, and there's, sorry, with that, and there's also another level down there. So it's multi-level with very complex geometry. Looking around, and now I'm missing the animation, around the park, we can see that the damage is partitioned on two scales. We have the global scale. The global scale is a scale of tens of meters of cavern that has collapsed. Here we can see this is the central, it's called the pit or the yard. It's a very large, several thousand meters, square meters area. Formerly it was a cavern complex, but now all the remains are vertical walls and one big former supporting pillar. And here we can see the damage, sorry for that the damage that was accumulated over the years until it has collapsed. And here we can see the remains blocks of the roof. A smaller scale of only of local impact is a scale when, as we saw in the first slide, is a scale where we see newly formed, I mean this post-excavation, it could happen 1,000 years ago, but newly formed tensile fractures, you can see here a tensile fracture, which are in an association with pre-existing planar joints, which, as I told you before, are tectonics pre-excavation joint. And by the morphology, sorry for that, by the morphology of this joint, we can even pinpoint the exact nucleation point where this joint has nucleated and why. Now, being the case that we have a global collapse, which has something to do with the collapse of supporting pillars, which eventually leads to the collapse of the entire system, then we have a local collapse, which these collapses can be quite big. It can reach tens of cubic meters of material that are collapsing, but they have no implications meters or 10 meters apart. So they are local. Using this data, we have decided that we have to go on two scales, different scales, to analyze the problem. One scale is the large scale, looking at the entire complex as is, using continuum approach. And the other scale, the local scale, is to incorporate discontinuities into the mesh and solve it locally. On top of it, we also have performed in situ monitoring using different methods, which I'll describe shortly. And also structural integrity of the pillars, which is these are still initial results, and eventually we integrate the all data together. So let us begin with in situ monitoring. Okay, because I lost my animation. So beneath this nice picture, there is a layout map of the Bedgovrine caverns, and there are locations of joint meters which were placed to monitor the displacement, the shear displacement along the joints. Okay, it was placed here in the main cavern or the main hall of the northern cavern. I don't think that we can see them here because they're quite small, but they are monitoring there are 8 different joint meters. There are also the temperature meter and humidity meter in here, and they're all located in, to our understanding, critical locations. So let us look now at a typical result. The horizontal axis is time, starting in June 2008 and to our times. The left vertical axis is gauge displacement, is the displacement, and the right axis is the temperature. The red line here is temperature, and we can see the temporal oscillations. The temperature is going from 30 degrees in the summer down to about 10 or even lower in the winter. These lines represent 3 displacement gauges, and as we can see here, basically they don't do nothing. the span or the amplitude is somewhere over the 5 years is plus minus 0.1 millimeter. Not much to tell about. There are other four, which perform essentially the same in other locations, and only one joint meter exhibit some displacement, permanent displacement, but again to a scale of up to or less than 1 millimeter over more than 5 years already. And when you look at it, you can see that it also responses to temporal changes of temperature, but it has an ongoing trend of convergence. Now, this can be disturbing if the magnitude was, let's say, several millimeters per year, but here we're accumulating displacement of less than a millimeter in 5 years on an average 0.2 millimeters over a year. It's no more than a creep along the joints. What we can deduce from this picture is basically that the joints are locked. Okay? There's not much. The story to tell about it is not a big story. Okay? There are some displacement, but it eventually leads to nothing yet. And I can go on more and to elaborate about the temperature displacement relations, and we can see here the displacement meters named from ND2 to ND8, and they're all oscillating over an average value of 0. And the only one that is working to some extent is joint meter that's called ND1. And we can also see that there is a slight deterioration of the joint over the years because the slope of the temperature displacement linear proportion is getting bigger, but again it is with the same magnitude of scale. So again, at this point at least, at this point of time, we are not disturbed with the displacements along joints in the caverns. This is quite a good news. Okay, these are good news, but this is not all the news. We also use NanoSeismic monitoring to detect shear displacements and brittle failures within the caverns in those places that we cannot measure them with our displacement gauges. And basically these are seismic mini arrays which are deployed on the surface of the topography. The caverns are down there. You can see here. This is one pit, and there's another pit, but we are atop of them. And each mini array is comprised of a central 3D geophone with 3 peripheral 1D geophones, and we have put 2 mini arrays in an implicated manner just to enhance our detection. And well, this is a nice method, and we've done some very basic, very simple calibration. We send our student down into the cavern, and we ask him to pick up a stone, and then just to shear it across a joint, and try to see if we can detect this event using seismic tools. And the answer is yes, we can do that. Here we can see traces for one of the central geophones, the 3D geophones, horizontal and vertical. And this is time, this is frequency content. Basically, we are looking at the time trace and the sonogram of the time trace. And we can see here that when you have an event of such a sort, there's an energy concentration at the higher range of frequencies, about 75 hertz, and almost everything else is just noise. Another type of mechanism, of failure mechanism, can be brittle failure, and here I show not measurements from the bed Gouvry area because they are less pronounced, but from another region that was monitored using this technique. And this is a monitoring of a failing calcareous sandstone cliff somewhere north of Herzliya, if I'm correct. And here you can see again the same picture: time, frequency content, time trace, and energy. And when something happens and there is emission of energy, you can see the energy concentrated in a very narrow frequency band. So our approach was a bit different. We are deploying the mini arrays on top of the caverns, and then we leave it there for about 2 weeks, come back and try to pick up the events. And the events are there, and we have detected strong and weak events. You can see here the magnitudes. The magnitudes here are as equivalent to minus 2.4 and minus 3.8 local scale magnitude. It's almost nothing. It's very small bursts of energy. Actually, the ones that we can detect are somewhere around minus 2.5 on average, and our location is not so good because we only can determine the location or the nautical location in increments of 5 meters, taking into account that we have about not more than 20 meters depth of the caverns, so it's not a very high resolution. But anyway, we know that there are events. So if I'm plotting one campaign of monitoring, which is about two weeks, these are the arrays, the diamonds, the red ones and the green ones, the location of the arrays. This is the floor map. Oh, now we can see also the locations of the joint meters here, and D is code for joint meter. And here, with the pluses, we can see those events which we could locate within these 2 weeks of monitoring. And it's about 30 something. Not the series, the TV series, but about 36 or 37 events which took place over 2 weeks. Now, if you look at the time, at the rate of production, or maybe I should take an digression, during one of our campaigns, not in the cavern itself, it's 300 meters apart, there was one event where a big joint suddenly developed overnight. You can see it here. At the same, in a matter of 2 hours since they have informed us that a big joint has developed, we have relocated our equipment from the cavern side to this side and tried to monitor at least the decay or the die out of this event. Okay? Joints are growing quite fastly, but at the end they stop somewhere where the energy allows them. And we hoped, and to our good luck, I think that we have succeeded to capture the dying event of this joint. And now we can look at the temporal distribution of 2 different types of events. On the left side, it is the static events. This is our monitoring campaigns, 2 weeks each time. And on the right side is the dynamic event. And here is the horizontal scale is time since first recorded event in seconds. And this one is the event rate. Both of the scales are the same. And here we can see that when looking passively at what goes on over the big cavern, it's about the same, very low, 10 to the minus 4 events per second. Basically, some noise, something is going on, some small fractures do develop, but not much to tell about again. On the other hand, here, at the dynamic event, and we have to recall again that I'm talking about the dying out of this event, okay? You can see a very nice trend of a decay. It begins with a higher production rate. The rate here is 10 to the minus 3, it's relative to 10 to the minus 4 here, and then it decays to the 10 to the minus 4. And we can even plot a kind of an only low decay low here, which probably, if we extend it toward the initiation or the beginning of this event, the production rate was much higher. So the conclusion from this plot now is that at the current time, present time, there's not too much of a brittle failure goes on in the material that surrounds the bed covering caverns. So, okay, the joint displacements, they are okay. Seismic monitoring shows that things are pretty okay. Okay, some things goes on, but with a very, very low amplitude and a very, very low rate. But still, things go wrong from time to time. Things collapse. It was in 1997, but from time to time, we also see small blocks falling from above, and some pillars are deteriorating over time. So, okay, what goes on? So, to answer this question, what goes on, we should first try to find what is the state of stresses around the caverns and within the caverns at present geometry. And to do so, we have built a 3D model, which we later incorporated into a finite elements model, which I showed shortly. And here we can see that we have done it in a very simple approach. We didn't use techniques like LiDAR and so on. We know that these are the entry pits, and each cavern is an ellipsoid, so we can find the radii, and we have measured the height. So eventually, using our best judgment, we have created a structure of overlapping ellipsoids, belts. We have excavated these belts with the material, and we performed a finite element analysis, and we can see the grid here. And the grid is a very elaborate one. You can see here the structure of the grid. It's not a uniform grid. It is a grid that is very dense in the vicinity of the caverns. We use tetrahedral elements 1 meter size, and then going out to the boundaries, the grid is getting bigger and bigger, eventually 15 meters tetrahedral elements. The overall size of the model is 300 meters by 300 meters by 30 meters depth, and the total number of degrees of freedom is more than 6 million. Okay, this is a very large model. In order to solve it efficiently, we have assumed that the material is elastic, which is in a way, it's something that I'd say it contradicts my beginning of the talk. But if you take into account that there's no story to tell about the joints, and the joints are maybe of a local scale, so we can safely, at least at this point of time, safely assume this is all continuous, and we take it as elastic, and look at the stresses. Now, here, okay, I lost some quality here. In the same manner, if you want to look at a local scale, we can pick every single bell-shaped cavern and introduce joints into the grid. This is what we have done here on the local scale. I have to apologize for the quality of the drawing. Here, this is the joint, and this is the cavern here. It's not seen so clear. And again, here also, the grid is structured such that it is very dense in the vicinity of the cavern and along the joint, and it becomes larger and less denser when we go out. And the interesting thing about incorporating joints into the finite element is that the time scale is different. Using the same geometry and the same grid structure, but without the joint, and time per se is not of importance because it depends on the amount of computational power that you have. But let's say this one was about 1.5 hours to complete the calculation without the joint. Once that we have introduced the joint, it's rise almost by 20 times. Okay, a single joint within a dense finite element mesh has not doubled, but enlarged it by an order of magnitude. So introducing even more joints will complicate it furthermore without, let's say, any benefit for us. So locally, we can solve it with 1 or 2 joints and look at the exact stress distribution close to the joint, but if we go global scale, we have to discard the joints and use it as finite elements in its continuous mode. The material properties of the Maresha Chalk is well known. I have studied them intensively, others also as well. This is a very light material. Its porosity is about 60%, its density is about 1.1 grams per cubic centimeter, meaning that if you throw it into the Dead Sea water, it won't sink. Okay? You throw a rock into the water and it won't sink. Okay? It is very shy in strength and stiffness. The compressive strength, and it depends on the direction, it's an anisotropic. It's about 9 megapascals if it's normal to the bending planes, and it's within the bending planes, and it's 6 megapascals when it's normal to the bending planes. And just to give you some kind of reference, the standard concrete is 30 megapascal. This is its strength. So it's about 3 times to 5 times weaker than concrete. Also very important, it is the tensile strength, which in most rocks, also in concrete, it's about an order of magnitude and even more lower than its compressive strength. So in tension, it's not more than 1 megapascal in the plane of symmetry, in the bending plane. And actually we couldn't measure it exactly in normal, but back calculations show that the strength, the tensile strength, normal to the bending planes are as low as 50 kilopascals, 0.05 megapascals. The elastic properties are given here. Well, all of these, except of this one and this one, were measured. Other ones are calculated using theory of elasticity. And more important than the values per se, it is the effect of the environmental conditions make this material very, very interesting. In the graph, the plot on the right side, you can see here the strength of the material as a function of water content, W. And this work was done by the Rednik and Shechadi in the Technion. And you can see here very nicely that even higher water content, the rock loses strength very rapidly. In some cases, the rock loses about 50% of its strength, given 10% water content. Meaning that with some increase in water content reduces the strength of the rock material. And this has to be accounted in the analysis. We cannot incorporate it as is into our model, but we can account for it in our interpretation. Another thing that we have to remember is not written here, that all of these tests that were done to determine these constants are done on very small samples. Some of them are as small as 50 millimeters, something like that, cylinders of 10 centimeter length, that's all. Not more than that. So if you take into account that if you enlarge the scale of the sample, then you will get even lower values for strength. And if you take into account scale and environmental impact, so the nominal strength of the rock is very, very low. It's not what is written here, but here it's, okay, for our purposes, it's more than enough. And we shall see it shortly. Now, here it was a very nice animation that shows the results of our model, in which I show what I find it a very nice name, a numerical CT. We just make slices at different heights of the model and each direction that we would like to, so we can examine the stresses at every level, at every point, every element that we are interested in. And here, for example, we can see the stresses in the arches. What are arches? Arches are the overlap areas of adjacent covers, as we can see here. These are teeny elements, and naturally they have a very high stress concentration here. We are also very interested in the stresses which are found in the two supporting pillars, which I have showed you before in the photos. Because these are critical for the stability of the entire system. So these are nice pictures. This is also nice pictures, again. but we should put some numbers in a short time. And here we are now looking at, this was the global model, and we are now looking at the local model. And we have modeled this specific cavern, which we have seen before, with this tensile structure here, and there's the exposed pre-excavation joint here. And now looking at approximately at the same angle, but with the material here still intact, we can see that high stress concentrations, tensile stress concentrations are found here, and they are found here. And the exact number here are of listed importance, but the location is very important because these are pretty much the same locations at the initiation point of this structure, meaning that it began here and it grew up towards the surface. And also here, we can see very extensive damage. We can also see it here. So basically, introducing a single joint will give us the right stress picture in its vicinity, and that's what we should do for in each place that we find an intersection of joints and free surfaces. So before I'll put some numbers into the scheme, I would like to show you an initial result from ground magnetic radar, which we used to survey the pillars within, that support the entire roof of the caverns. And here we can see this is time in nanoseconds. This is meters from 0 to 4. This is the width of the column, and these are traces. And very similar to seismic traces, we can draw very simple synphasic lines that show that there are, let's call it reflectors, discontinuities within the pillars. And you can see these discontinuities are probably joints. Okay, and you can see this is a semi-automated interpretation, and we can see that there are several very big discontinuities which are found within the pillars themselves, meaning that these pillars are not intact, and they probably do not or cannot take the load as is. It's coming out from our calculations. Okay,
what's the scale?
Here?
Depth scale, if you convert it.
If you convert it to depth, it's about also, let's say it's about 2 to 3 meters.
All of it.
The entire optical scale. So probably we're looking at the first 2 meters. So let us put the numbers. Okay, these are the results of the global analysis. And here we'll look at 4 different scenarios and stresses ensuing from these scenarios. The orange one, it is the current situation. We have pillars 1 and 2 at their prime state. Okay, they are not damaged, everything is fine. The gray is without pillar number 1. Let's assume that pillar number 1 is no longer supporting the roof above it. And let's calculate what's going on. The green one, it's the same exercise but without pillar number 2. And last and least is the worst case scenario here in the maroon color. Let us assume that both pillars are gone. They are not supporting pillars, they're just there, but they have no mechanical influence or impact. So, the vertical scale here is the tensile stress within the arches. These are the number of the arches, 3 and 5, 3 and 4 and so on. These are the numbers of the overlapping caverns according to our mapping. And we can see here that if we take our best case scenario, at no one of the arches, the stress is higher than 250 kilopascals. And here is the laboratory strength value, about 1,000 megapascal. And here are 2 boundaries which define size effect or water content reduction by 10%, meaning that we reduce the strength by 50%, either this effect or the environmental effect. And the worst case scenario, if we take into account both effects, both environmental and scale effect, we are now at somewhere about 350 kilopascals tensile strength. Anyhow, in any case, if both pillars are intact and are performing well, everything is fine because we are very low and well below the lowest assumed tensile strength. Now, let us remove mechanically pillar number 1. Now this is the gray bars. So now we can see that from this orange scenario, we now have an increase in 1, 2, 3, 4, 5, increase of stresses in 5 out of these 7 arches. And in some of them, like say in arch 7, 8, we are well above the minimum or even the nominal strength of the material. And here we are very close to it. Now again, if you do the same exercise but by removing pillar number 2, only in 1 arch, you see an increase of stresses, which can bring it close to failure. Naturally, if we remove both pillars, the stresses go high, as high, even higher than the lowest strength and even the nominal strength. So removing the 2 pillars mechanically will induce close to failure or close to strength. Let's rephrase it, close to strength values of tensile stress in the arches, meaning that some of the arches will begin to crumble and to collapse. What happens within the columns when I remove either one of them? So this is the pillar, number 1, number 2, number 3, and the color code is the same. So if I'm, for instance, even if this scenario where the 2 pillars are intact and they are taking their all responsibilities, both of the pillars are now at least above the minimal strength, the nominal, and one of them, number 2, is approaching to the probably the realistic state of matter of bed covering area. Now, if I remove pillar number 1, and now only pillar number 2 is taking the load of the entire system, then the vertical stress within are even more increased, and when I remove it in turn, then it increases again and again. So basically this is like in a cascade. If I remove pillar number 1, pillar number 2 gets the entire load, and then it could begin to fail. And if I do the same by removing pillar number 2, here is the impact. And if you go from here to here, let's say by removing pillar number 1, so I'm overloading pillar number 2, and I'm bringing some of the arches to failure. So in this case, the most critical pillar in this governance are pillar number 1. If pillar number 1 is not performing to its full capacity, the entire system of governance is in danger. So I'm almost close to finishing line. Some more nice colors and easy lines. This is what basically we're now looking at the stresses at the top of the caverns. These are pillars number 1, 2, 3. These are the caverns, and let us look what happens when we remove pillar number 1. It's not here. So here we have high tensile stresses. Okay, the red lines are tensile stresses, which form or which begin introducing a new formed joints here. And here we have a high compressive strength in the roof, at the top of the roof, but from a mechanical point of view, it has to be compensated by the same magnitude stresses at the roof of the cavern itself, so meaning that everything is beginning to collapse. And naturally, if we remove both of them, then it will collapse at the end. So, to the conclusions. We have come to the conclusion that we can partition the mechanical analysis into 2 different scales. The global scale, which is continuous and elastic, and is supported by our observations with joint meters and NanoSeismic monitoring. And we can, if needed, we can capture the stress redistribution near joints and their local, the local impact. We also see that our initial observations support the localization of damage in the pillars. The GPR data shows that the pillars are not intact. I cannot say at this point of time that they are crumbling or they are falling down, but they are not at the prime state, this is for sure. And as for the bed rim covers themselves, I safely say that the geometry as is now is marginally stable, and further degradation and loss of bearing capacity of pillars number 2, 1 and 2 will eventually lead to a total collapse of the cover, which means that these two pillars have to be reinforced mechanically if this this cover is to be remain to be open. Now, very nice reservation. It was Niels Bohr that said that accurate predictions are very difficult to make, especially about the future. This is the reason why most scientists and engineers do predictions and not predictions. This is the case that I have presented here. So, but you know, this is Niels Bohr and this is me, and so I'm in good company. And Justin's ending remark, I don't know how many of you are familiar with the Rambo trilogy. Yes, and it is not just a joke. This is from
The trilogy anymore.
It's not trilogy? I missed something?
Not anymore, yes.
Well, I'm getting older. So basically, it was a trilogy about a few years ago, and the second part of the trilogy, there's a very nice, there's a very long, lengthy scene of John Rambo wiping out the entire Spetsnaz Russian commando within the bedroom rim covers. So these covers are not only locally famous, they are of global fame in Hollywood as well. And at this point, if you have any questions,